Ladies and gentlemen, dear colleagues, welcome. My name is Zdeněk Hanzálek, and you are watching the 41st talk of the scheduling seminar. Today, I'm happy to introduce Rainer Kolisch. He is a professor of operations management at Technical University of Munich. During his career, he worked in different universities in Darmstadt, Dresden, and North Carolina, for example. He made his PhD in '94 at Kiel University with Andreas Drexel. And he was on board of many operational research journals. One of them is Operational Research Spectrum, when he was for a long time editor-in-chief. By the way, he was listed among 10 most influential professors in Germany and Austria and Switzerland in 2005. So if you do operations research, you can become a big professor as Rainer. Rainer, it's great to have you here, and please go ahead.
Well, thank you for your kind introduction, Zdeněk, and thank you, the board and the organizers of the scheduling seminar, to have invited me. I'm very happy to present some work which I have done over the year, which started in 2003, and I have been working on this topic over the time, not only, but it always has been one field I have been interested in. Okay, so before we can start, there are the commercials, and the commercials is we are happy to host the International Conference of Operations Research organized by the German, the Austrian, and the Swiss OR Society. From September 3rd to 6th in Munich. It will be a great conference. We expect about 800 to 1,000 researchers. So you're welcome to come to Munich. We are looking forward to this. Okay, now we are moving forward to my talk. The outline is as follows. I will shortly introduce the FRCPSP, which stands for Flexible Resource Constrained Project Scheduling Problem. I will go into two different solution approaches. Well, one is more kind of a survey of MIP formulations of the problem, and the other one is a metaheuristic. I will look into instances and then go to some applications, in particular two I have been happy to work at, and then I will end with some research opportunities. The overall kind of scope of this talk and the flavor of this talk is more from an application point of view. So I've been working a lot with using OR in order to address real-world problems. And this will be the view I'm having here. Also, I try to give more a survey of the field, not so much a very deep dive into some specific aspects. And finally, I focus on the work which I have been doing in this field, but of course others have done a lot of work in this field, and with this field I mean the FRCPSP as well. Okay, so we start with the very famous and known scheduling problem, resource constrained project scheduling problem, which is one of the prominent problems in the field of scheduling. It's already a very rich problem if you compare it to single parallel machine problems or even problems like the flow show problem. And it is about a set of tasks or activities. Each of these has a predefined processing time and a predefined requirement of one or several resources would be specified in terms of the units used when processing the activity. So if you look at the activity 2, for example, which has a duration of 4 and a resource requirement of 3, then you see here we can depict each of these activities as such a rectangle. That is the duration of the activity as well as the resource demand. In this case, with respect to one resource is given. And this is subject to precedence constraints between the activities, which state that you cannot start an activity before you have finished all of its predecessors. and subject to a resource constraint, which for each of the resources. So here we have a capacity of 4, and these two things we have to take into account. And then the only decision which has to be undertaken is the scheduling decision. That is, for each of these activities, we have to say when should it start, such that some objective function, which very often is a make span, so it's the overall time we need to undertake all of these activities, is minimized. This problem is already quite known to be NP hard, and a lot of research has been done on this work. So this is where we start. And now we are moving from the RCPSP to the flexible RCPSP, which we abbreviate as FRCPSP. So we have the scheduling component, but now we have, for each of the activities, we have a resource allocation component. And it's according the following constraints. We have an overall work content, and the overall work content is, when you look at it from the RCPSP, it's the duration times the resource demand with respect to one resource. So it is the area of this rectangle. This is the overall resource demand. And now, instead of predefining the duration of the activity and the constant resource demand over time, once it is processed, we have it's in our decision how we allocate this resource demand over time, subject to a number of constraints. First of it, if you allocate resources to the activity, that is, if you put it into process in a period, it has to be at least of this amount. So we have a lower bound on the allocated resources, and we have an upper bound of the allocated resources. We have to allocate the total resources, the total work content, within a given time window. There are no idling periods which are allowed, so we have a no preemption case. We have the so-called minimum block lengths. That is, we have to have a constant amount of allocated resources for L periods, and I will show you this in an example. So these are the rules which apply. These are the constraints which apply for the resource allocation problem. So now we have the resource allocation problem plus the scheduling problem. So here are some examples for the resource allocation. So we assume we have a work content of 12, and this has to be allocated in a time window. Let me just make this a little bit smaller here so I can see what I have on my slide. So we have a time window here of length 6. So we have to use 6 periods in order to allocate those 12 units. We have a minimum resource allocation per period of 1 if we allocate, and a maximum of 3. So for example, here you see in the first case, we don't allocate in periods 5 and 6. So here, of course, the bounds don't apply, but here they apply. So here we are at the maximum throughout all 4 periods. So, and then this would be one possible way of allocating the resources. And here we see already this is one possibility. And this would be, if we do this for every activity, then we have more or less, we have the RCPSP case. So the RCPSP is a special case of the FRCPSP. So here we have another possible allocation. We see here the minimum block lengths. We have to have constant resource allocation for 2 periods before we can have this jump in the resource allocation, another 2 periods for resource length 2 for this minimum block length. Here's another one, and a fourth possibility. So this gives you an idea of the allocation problem. Now, if we put these 2 things together, so we have here a project, we have here the work content, which has to be allocated, and then this could be now a feasible solution. And here you see the 3 decisions which have to be undertaken. So we have the precedence constraints. So for example, between 1 and 2, we can only start 2 once 1 has been finished. We have the resource allocation decision. So we have to determine the profiles for activity 1, for 2, and for 3. And we have to take into account the resource constraints, which here is a limit of 6. So this would be one, this reflects kind of the richness of the problem and would be one solution. Now, in the work I have done with my co-authors, we termed this problem the FRCPSP. Norbert Trautmann and his team at the University of Bern have also done a lot of work in this field, and they call it the RCPSP with work content constraints, which is a different way of well, defining this problem, but essentially they are looking at the same problem. There's a subtle difference, which I will mention in a second. Okay, now what variants are there? And they're basically two different aspects which can be changed, and this is the time line. Do we look at a continuous time or do we look at a discrete time? Also it's a resource allocation. So do we allow a continuous allocation of resources or do we allow a discrete case? And Norbert Trautmann and his team, they are looking at this discrete case. So they are looking at discrete time and discrete resources. And they are looking at a partitioning problem where you have to allocate exactly the required amount. You're not allowed to allocate more, whereas the problem we are looking at, the discrete time continuous resource problem, is a covering problem where we allow to allocate more resources than required by the problem parameter W. So this is a problem I will be looking at it most of the time now in the following. So here's some work which had been done, and throughout the presentation I will point out some more work. Now, where does the FRCPSP is in the project scheduling landscape? As I have said already, it is a generalization of the RCPSP, and as such, a generalization of many specific scheduling problems: single machine scheduling problem, parallel machine scheduling problem, job shop problem, flow shop problem, simple assign line balancing problem, and many more problems. It is also a generalization of the multimode RCPSP, where we have different predefined ways of processing activities, all defined typically by these rectangles, that is, given duration and given constant resource demand. So, and as such, the problem is, of course, NP hard, and it is harder than the RCPSP because we have this allocation decision as well, and so typically the RCPSP can be modeled as a MIP where all the variables are binary if we go for discrete time. And the FRCPSP we are looking at has always these is a MIP where we have the binary and the continuous variables. If the time windows are sufficiently large, then we can always derive a feasible solution in polynomial time. Okay. Now, what solution approaches are there for the FRCPSP? There have been a number of different MIPs which have been proposed, starting with the first, which we did in a application study where we kind of came up with the idea of these resource allocation problem embedded in the RCPSP. And later on, Baumann and Trautmann and his team in general worked a lot in this direction. So they provided MIPs, they provided insight, and some work had been done along this line. And then in 2014, together with my co-author Anurag Naba, we did a comparison of different MIP formulations which had been introduced to the literature for the general RCPSP for scheduling problem. We applied them to the FRCPSP, and I will report on this. And then there are a number of heuristics which have been proposed, starting with simple priority rules, and then different meta-heuristics, most notably genetic algorithms, and recently also math heuristics. And I will look at a hybrid meta-heuristic with one of my PhD students, Ritschler, has done, which is kind of interesting because it shows how we can apply things which we know from the RCPSP, which we can apply to the FRCPSP. Okay, let's start with the MIP formulation. So this is now based on the work with Anurag Nava. And kind of the foundation for this work is what Christian Antique and his team has been doing in Toulouse. They came up with this nice survey of different ways of modeling the RCPSP with different concepts using different type of variables, most notably the pulse and the step variables. And so let's look at how can we model the resource allocation problem. And so we start with the binary variable Z, which is the on-off variable. It will be 1 or is 1 when the activity is in process. So you see here, activities in process from 2 to 7, and hence we have the 1s here in the Z, and otherwise we have a 0. Then we go to the classical pulse variable, which also already had been proposed by Pritzker, which turns 1 if the activity is started and is 0 otherwise. And then the extension of this is a step variable, which turns 1 if the activity has been started or is started. So then assume we have this jump to 1 if the activity started, and we will remain with 1 for the end of the planning horizon or the time window. Then we have the kind of the twin of the X variable is a Y variable, which turns on if the activity is finished. So here, the way we model it in the last period when the activity is processed, it will be 1, 0 otherwise. So it's again a pulse variable. And then the extension to this towards the step variable is we turns 1 in the last period and will stay 1 through the end of the time window or the planning horizon. And then we have to keep track of the points in time when there's a change in the capacity allocation, because remember we had this minimum block length. So we have to measure how long we have the same amount of resources allocated. So for how long, of how many periods in order to enforce this constraint. For this, we need the delta variable, which turns 1 if there is a change from period t-1 to period t in the resource allocation, which you see here. So there's a change when the activity starts. Then when we have the first increase in the allocated resources, there's a change when we have the decrease, and then when the activity is not processed anymore. Okay, these are the binary variables. Then we have some continuous variables. We have the Q, which is the amount we allocate, the amount of resources we allocate. So here at the beginning 1, then we allocate 3, and then we allocate, this is a wrong, this should be a 2 here. There should be a 2. So 1, 1, 3, 3, and then 2, 2. And then we have this cumulated intensity based on the KISS model by KISS. And here we have, so how much of the overall work content has been performed until the period. So we start with 01, 02, then we have 05, and so on and so forth. And at the end, we have the 1. And I think there should also be a typo, because I have the 1s here and I calculated this with Excel. So this should be, these numbers should be different. We'll look at this after the talk. And then finally, we have the starting period, and the starting period here, of course, is period 1. That is, we're looking here at periods, beginning of period 2, we start the activity. So these are the different variables we are having. Now, based on these variables, we have looked into 4 different models, which we created by looking into the literature and combining different concepts. And the first one, and so it's FP stands for flexible, and the DT1 is discrete time, model 1, 2, 3, and 4. This is how we came up with this abbreviations. The first one is using those on-off variables, which indicate if the activity is in process or not. And similar formulations you can find by Klein for the RCPSP and by Baumann and Trautmann for the FRCPSP. So here we are using, so this is this formulation here, and here we are using the Z variable. And also we are using this indicator of the change of allocated resources. We are using the amount of allocated resources, the Q, and we are using for the objective function, the Cmax, because we are minimizing the make span. So we have another continuous variable, which I didn't mention, the make span. Second model is based on Ranchbar and Chianfa. It uses the pulse variable. So we are having here the X, 1 if the activity starts, and we are using the other pulse variable 1 if the activity completes. We are using the indicator of different resource allocation, the delta, and Q and C max. The third one is due to Bianco and Caramia, a model which I have proposed for the RCPSP, and it uses the step variables, X, A, so turns 1 if the activity has been started or is started, and then also the Y, the step variable Y for the end, and then we have this continuous intensity variable, which measures how much of the work content has been done until period T. And finally, the model based on Sabze Pava and Sayed Hosseini, they are using the on-off variable, the Z, and the continuous start variable, S, and then also the indicator for change in the resource allocation, Q and C max. So these are the different variables. I will not go into the details of the models. Basically, the models using these variables have parts which are common between the models and parts which are different, which is kind of what we, of course, what it has to be. And if you are interested here, you can look in the paper by Naba and myself, which has been published in 2014 in EJOR. So now looking at the size of the models which we come up with, we see that in terms of size, there's a number of variables, a number of constraints. The first model is the best one in terms of the of these numbers. However, in terms of the density of the matrix, we see that the model 3 has less non-zeros. So in that respect, the model 3 is better, and these are the two. So the bold ones are always the ones which have the best numbers. And you see that, so these two models stick out 1 and 3. Now, if it comes into the performance of the models, there's a clear winner, and this is the model 3, which gives us the best results in terms of number of problems solved, number of feasible solutions, gaps, and so on and so forth. So these models, throughout all the indicators which we use, gave the best results. This is in line with what we've seen, where they always also had those step variables, and those the formulation of the step variables gave the best empirical performance throughout the different models, under certain assumptions about the parameters and the data. But for the majority of the problems, these were the best formulations. And so here, this is kind of the marriage of the step approach plus then the intensity approach based on KISS. Okay, then moving forward to Metaheuristic. So this is work which we have done with Martin Tritschler, a PhD student at Technical University of Munich. And so what he did, he had to devise a metaheuristic for the FRCPSP. And there were three main components. First of all, a parallel schedule generation scheme, which we adapted to the FRCPSP. Then a general genetic algorithm based on the one of Hartmann, which we adapted, and then variable neighborhood search-based transfer of resources in order to improve solutions derived by the genetic algorithms. So let's look first at some things which have to be considered when generating solutions. First of all, a greedy resource might not be optimal. So what you see here is that activity 1 and 2, they can be both processed in parallel. First information here is the overall work content, and then we have the lower bound and the upper bound of the resource which we can allocate per period. And you see here that allocate the maximum amount which is allowed, which is 5 per period, and we do this throughout the entire duration of the activity in order to minimize the process duration. So the processing time of 1 is minimized if we are maximizing the resource allocation throughout the entire duration of the activity. So the minimum duration of this activity 1, taking into account a work content of 20, and a maximum resource allocation per period of 5 is 20 divided by 5 for periods. Okay, so this would be a greedy approach. We schedule activity 1, and we try to allot as many resources as we can, and then we would schedule activity 2, leading to this duration of 6 periods. Now, if you look on the right, and assuming that we have a resource of a capacity of 7. Now, if you look here, we first schedule activity 1, but not with the full or the maximum resource allocated, which we would be allowed to, but less. And then this allows us to also schedule activity 2. And once activity 2 is finished, we can schedule the remaining work content of 1, leading to an overall make span of 5. So this shows that we might not agree, or assigning resources in a greedy fashion, minimizing the duration of a specific activity might not be optimal. That is the first observation. Second observation, early start may not be optimal. So here we have again an example, and you see now that here once activity 1 is finished at the end of period 3, we could schedule activity 2. Now activity 2 here, we are assigning let's see. So we have an overall resource work content of 9, and we have 1, 2, 3, 4, 5 periods. So 9 divided by 5. So we assign 1.8 resource units per time. This shows as an example that we have this continuous case, which I'm talking about all the time. So the continuous resource allocations allowed here. We are not restricted to the discrete case. So we are assigning 1.8 units. Now we have a minimum block length of 3, and due to this we have to go 4, 5, 6, and then we could change. But now adding more resources to this would not reduce the overall duration of this activity, which is 5. So we end up with this due to the block length mainly. We end up with a make span of 8. If we would have delayed activity 1 to the start of period 5, we could have assigned the maximum amount of 3 resources per period, and this would lead to a duration of the activity of 3, and thus we would be finished by the end of 7. So early start may not be optimal. Now, How does this heuristic works? First of all, we are using this an activity list on encoding, which is a sequence of the precedence feasible sequence of activities in order to state the priority of activities when they are scheduled. We use a resource allocation limit list. So this is basically information which tells how much resources are allowed to be assigned to that activity in the processing periods, and it works as follows. So we have this row here, and the row is you see this here. This is Q is the amount of resource which are allocated in a period. W is the total work content, and D underlined is the minimum duration of the activity, which we can derive by dividing the overall content by the maximum resources we are allowed to allocate per period. So this is a minimum period, and then we have this row here. So if row would be 0, then we would calculate the total work content divided by the minimum period, which would give us the maximum resources we have to allocate per period in order to realize the shortest processing time. If row is larger than 0, then this leads to less resources which are allocated. So the row governs the amount of resources we are allocating to the activity. And then we have a start delay list, sigma, which tells us how much should we delay an activity. And to give you an example on this, how this works, the encoding from a solution, which is defined by these 3 lists, activity list la, the resource allocation row, and the delay list sigma. So look at this example here. So in period 1, we have to start scheduling, and we are looking into the activity sequence list, and we pick the first activity, which is shown there, which is activity 1. So we schedule activity 1. Now, how do we schedule it? First of all, we look, should there be a delay? So we look at the kind of the updated earlier start, which is period 1, plus the delay of sigma. So if we look at the delay here, is it 0? So we start the activity as 1, which we see here. So activity 1 is started in 1. So now how many resources should we allocate? So for this, we take the minimum of the available resources. In this case, this is at the beginning 3. The work content of activity 1, which is 3, divided by the minimum duration. The minimum duration now is the work content divided by the maximum resource we can allocate per period. So the minimum duration is 1. Okay, so this you see here. So this is there you see the 1, the minimum duration. And now we add this resource allocation information, or the resource. How did I call it? The resource allocation limit. Which is 2. So here now we add 1 plus a 2, and thus 3 divided by 3 gives 1, which we see here. So this information, the 2 here, is larger this is, as less resource will be allocated to that activity. So in this you see here, 1 unit is allocated. Now we do the same with 3. Now the only thing which differs here is that the leftover capacity now is 2. Again, we have this delay, this resource limit of 3, which we take into account here, which again gives a resource allocation of 1, which we see here. That would be in period 1. Now, jumping to period 4, we would select activity 2, which is the last activity which is selected. The start of that activity would be the updated start, which is the end of period 4, plus the delay, and the delay is here 1. So that would lead to a start in activity 5. We could have started it so 1 and 2. We have this precedence relation. So we could start 2 already in 4, beginning of period 4. However, we have this delay information, so we started at 5. 4 plus 1, 5. Now, how many resources do we allocate? the remaining resources, which are 3 here. We have the full resource available. And now work content divided by the minimum duration plus this resource limit information, which is in the case of activity 2, 0. So we can allocate now the full resources from the point of view of the activity and the availability, which is 3, which then gives us a make span of 7 periods, which is the better solution than if we would have scheduled activity 2 here right away in period 4. So this is how the mapping works with those 3 vectors. And the crossover is adapted from Hartmann. Basically, it's pretty simple. So the activity sequence list, we take, it's a 2-point crossover. We take the first until the first cut. We take the information here. So I have to be, we have to watch our wording. So it's not a mother and father anymore. Now it's parent 1 and parent 2 and child 1 and child 2. So this is, we take 1, 3 from parent 1, which is here. Then we cross out 1, 3 in the activity list of the second parent. And we take the next few not selected activities, which are 2 and 4, which we put in here. Then we cross out 1, 3, 2, and 4 in this list, and we take the remaining activities here, which would be 5, 6. Okay, so this is this famous crossover of Hartmann, which allows to take into account the precedence constraints which are implicit in the list. And then the other ones is quite simple. So in terms of the resource limit vector, we take the first 2 information from the parent 1, second 2 information parent 2 here, and then the remaining information from parent 3. And the same is done with the delay list, first 2 from parent 1, second 2 from parent 2, and remaining ones from the parent 1 again. And this is how it works. So it's an adapted 2-point crossover from Hartmann. And then finally, there might be the case that there are that we can improve the make span by moving resource capacity from one activity to the other. And we do this by resource transfers, where we first check which activities are on the critical path, which are non-critical, and then we determine all possible pairs of resource flows from a non-critical activity to a critical activity. Then we look into a variable neighborhood search, where we first do those realize only a single resource transfer, or 2 resource transfers, or 3, and so on and so forth. So this is there in order to improve then the solution derived by the genetic algorithm in a nutshell. Okay, some computational results. We compared this approach to an adapted genetic algorithm, priority rules, and serial scheduling scheme, and the results showed that the method was clearly superior to those other methods. We used the instances which have been created by Fundeling and Trautmann, and I will come to this later on. There is no comparison with the approach of Fundeling and Trautmann, because, as I said, the problem is has a little twist. It's a little different, because we have this in the Fundeling Trautmann, we don't have the covering, but we have the partitioning and the discrete case. So there's no direct way of comparing the results. So a question which arises, so what does a VNS, what is the value of the VNS? And we could show that the VNS helps in order to improve the solution. So we could improve 22% of the instances on average. We improved the make span by 1.34%. I mean, this is not that much, but it's clearly an improvement over the adapted genetic algorithm. Now, turning to instances, there have been, so far, there has been the set of Fundeling and Trautmann, which can be divided into 2 subsets. subset A, which is based on the PSP-lib instances, and then they modified them in order to take into account the work content, content constraints. And then there was a second set which they generated based on the Progen Max, which had been devised by Schwind, and it contains 2,400 instances. So these were the status quo in terms of the instances for the field, which were used. Devised for the discrete resource discrete case, but you can also use it for the resource continuous case. And then recently we have jointly with 2 PhD students, we have generated a set which comes from a real-world application in engineer-to-order production planning, and I will sketch out this application later on. So we have collected instances from them. So I will not go into these instances in detail, but they are there. So I will now move in the sake of the time to the applications. So there have been, the FRCPSP has always been motivated by applications, and it started when we looked at a optimization problem in the pharmaceutical research area in 2003. Until then, we had a number of different applications in different fields. And I think the strength of the FRCPSP is really that it allows to depict a lot of real-world relevant aspects of scheduling. So this is the problem which we started, which kind of made create the RCPSP. It was together with Christoph Schwind and a PhD student, Konrad Meyer, and 2 researchers from, at that time, Aventis. Aventis is probably the pharmaceutical company which had the shortest lifespan of all large pharmaceutical companies, and it started in 1999, and it had been well then merged with Sanofi Sinterlobo to Sanofi in 2004. So, and before it had been Höchst and Rhön-Poulenc. So a very short, brief time window for this company, and this was exactly the time when we came across a problem in the lead optimization of pharmaceutical research. And let me shortly sketch this out. So it starts with a substance which should lead to a potential drug very early in the research chain. So chemistry is modifying this substance. The modified substance will then be checked here in eADMET in order to check if the human body can cope with this drug. So there are no side effects, and it is checked here in terms of the in the disease groups where it is checked if the drug is effective. So if it cures the illness which it should cure, and this is done in a number of cycles, typically 15 to 20 cycles. So if you model this as a big network, then you have a multi-project case because you have a lot of different drugs. Each of these drugs is a project. And so in our case, there were about 20. And for each of these projects, you have between 15 and 20 cycles. And in each cycle, you have the chemistry work, which is done, and then you have the work in terms of effectiveness of the drug and side effects of the drug, which is done. And the work is typically work content work. So it's a number of units which can work in parallel. And the unit is typically, it's a chemical engineer, 1 or 2 chemical lab assistants, and the laboratory. And then they are working it. And then the question is, how many of those should we should do one specific activity over time? So here you see, this is always the work content in laboratory weeks. So these are 6 laboratory weeks. Okay, and the overall objective was to minimize the make spend. So this is how we came across the problem, and there we came across this work content, which we then depicted with this first formulation. Now, The second application I would like to show you is a recent work I'm doing with a PhD student, Robert Brachmann. And so we are looking at large machines for, again, in the pharmaceutical industry, it's packaging machines for pharmaceutical products. So basically here you have the pills which are going into the machine, just bulks of these pills, and then they will at the end you have them within the blisters, within the little packages, within the larger cartoons, maybe even on pellets. So and this is fully done automatically, and this is engineering to order production done in a mid-sized company in southern Germany. And so these machines are typically consisting of modules, and customer can make a decision which modules they want to have in their overall machine. And the modules then consist of project activities, basically, and you put together those modules. The overall planning horizons, which we are looking at, is about 1.5 years. And the work done in these activities is measured in worker days. So, for example, 30 worker days. And then if we would allot 5 workers, then we would have 6 days in order to accomplish the work. And the interesting thing is that each activity only requires one specific resource. So you see, for example, synchronization, which is activity 11, requires one resource, which is some synchronization when everything is put together and tested, for example. So this is specific. So there's no overlap in the used resources by the different activities within one project, but across all the project, of course, there is this overlap in the resource use. So basically, in terms of the resource constraints, activities of different projects are competing with each other, whereas within a project there is, in terms of the resources, no conflict of the activities. We just have the precedence constraints. And here you see the overall project network. We have 2 sets: the set of start activities of all the projects, the set of finish activities, and then the overall objective is to minimize the sum of the weighted so weighted across the projects, because you have more important and less important projects, and then again weighted earliness and alpha, we weight the earliness, and beta we weight the lateness, where kind of lateness is higher weighted than the earliness, and then we have the customer weight. So, and this is minimized. So we minimize weighted earliness and lateness. Model, the FPDT3, so the best model which we found out in the prior research. And the idea now is, since activities require different resources, what we can do is to only look at, because only these synchronous activities, they define the make span. So what we can do is determine the largest possible time window for these activities, and then only take into account the resources for the synchronization, reducing all the other resources. This is basically the idea, and this will give us a lower bound on the objective function. And you see here that by using this lower bound, we dramatically decrease the number of variables. As you can see here, in a short runtime, we can obtain quite good lower and upper bounds for this relaxed problem, which then helps us to solve the full problem earlier. This is the idea of the solution approach. And here are some computational results where you see that using the lower bound within the MIP improves quite well on the solution time. So in essence, bottom line, we not always to optimality, but we can solve real world problems with up to 140 projects for these machines with a standard MIP solver, in this case Gurobi, by using this lower bound. Research opportunities. So I think that there are a number of interesting research opportunities. First of all, we can improve on the MIP formulations. There has been, not only in this field, but in general, there has been a lot of improvement in the MIP formulations, because nowadays the solvers have become so powerful. And also, like the research with Christian Antique had done, we really improved on the insight we obtained in deriving good MIP modules, which then help us to solve the problem. And I think more can be done in this field. I think in terms of the meta-heuristics, we can improve further. And we can also improve, and this is not listed here, in terms of the insight we obtain into the model. So, for example, regularity of objective functions, which schedules are optimal. So we know the classical differentiation in active, semi-active, and non-delay. And so this is work which hasn't been done for the FRCPSP. And finally, I think there are a lot of applications down out there, and it's up to us in order to use FRCPSP and models based on the FRCPSP in order to address new applications. So before I end, I'd like to acknowledge the ones which have worked with me on this topic and inspired me by doing this. Christoph Schwind from Clausthal, Norbert Trautmann from Bern, Christian Antique from Toulouse, and here at TUM, Anurag Naba and Martin Tritschler, and Konrad Meyer, which was a PhD student at Darmstadt. Having said this, you find the literature here at the end, but I will not go into this. And now I will stop the talk at this point. Thank you very much.
Thank you, Rainer. It was really exhaustive. So now is the time for questions. I think everybody should be able now to unmute. So if somebody wants to ask a question, just go ahead. Before that, maybe I can ask you to go to slide number 9, where you show relations to multimode RCPSP. And I'm not sure if it's a real subset of your problem, because in multimode, you don't have the constant workload, don't you? You can have rectangles that have different width and height, but the overall area of the rectangle doesn't need to be constant.
Yes. This is correct. So under certain, you need to have certain assumptions.
Okay.
Then you can depict the RCPSP by the FRCPSP.
I understand that your model is more flexible, definitely.
Yeah. No, this is a little bit. This is not 100% precise. Yeah. Also, the MRCPSP allows, for example, the resource trade-off, which we don't have in the FRCPSP. So I have to be more precise here. Under certain assumptions, mild assumptions, I would say we can model MRCPSP problems as the FRCPSP, but we cannot model all of them. So in that sense, it's yeah, you're correct. This should be correct.
Okay. Yeah. And then you have mentioned on some of the previous slides that in Trautmann model they cannot use more units, or what was it? Like in
no. The Trautmann model, there is this constraint that you have to allocate exactly the work content to the activity. So you're not allowed to assign more to the activity, more resources than the work content. Whereas in our continuous model, we allow to assign more resources to the activity. So, for example, think about that we have there is I don't know, four units which have to be still assigned, and we have or let's say 3 units, and we can assign 2 units per period, but we have a minimum block length of 2. Then we have to assign 4 periods overall, and then we would be finished after 2 more periods. However, if this is not allowed, if we have to assign exactly those three, the remaining work content of F3, then we could not finish this within 2 periods.
I see. Okay. All right. So any other
So in that sense,
questions?
the problem looked at by Trautmann's working group is kind of more operational, and at the same time it is harder because you need exactly to meet the demand, and so it becomes this an additional combinatorial flavor.
Mm-hmm. Okay, and then I would like to ask you also about your experiences in incorporating different criterion functions and makes plan. In your MIP model, this tardiness criterion, is the performance much worse than with makes plan, or is it more or less the same? Or
to be honest, we haven't we have not looked at this. So because in the NABA, in the comparison of the MIPS with NABA, and also in the Metaheuristic, we looked at makespan, and in the application with in this engineer to order application, we just looked at the solving it with a MIP. We looked at this weighted earliness tardiness, but haven't looked at all into the minimizing the makespan. So my hunch would be maybe the earliness tardiness is even a little bit faster to solve than just the makespan, but this is just a guess. But we haven't done any systematic comparison on this.
My experience, for example, in RCPSP in constraint programming is that Cmax is much easier to solve. But this is constraint programming, which probably does a formalized decision problem for fixed Cmax, and then it looks for whether it's feasible or not, right? And if it's feasible, then it shortens Cmax. So Cmax is quite a good criterion for that approach, but summative criteria, which are consisting of several decisions, are maybe more difficult. So CP nowadays is, I think, a leading solution in classical RCPSP, at least to my knowledge. Have you considered also of using constraint programming on this FRCPSP?
We have so far we haven't done any constraint programming on this, but I agree that it has become very competitive, and this would be also an interesting field of research to look at it. Yeah.
Okay. Good. Thank you. So no more questions?
I have a question about some theoretical aspects. All of your problems are very much strongly NP hard. Nowadays, people have started to look at, by the way, research in Germany and Israel on fixed parameter tractability. So if you fix a parameter, then a problem may become polynomial. Okay. Now they have solved for some problems with precedence constraints, because very often in project scheduling, it's the precedence constraints that causes the problem, that makes the problem NP hard, besides some other things. And if you, with the precedence constraints graph, if you keep the width of the graph, so the width of the how wide the precedence constraints graph, if that width is a fixed number, so you don't let the number of activities go as high as you want, but the width is a fixed parameter, then there are scheduling problems that then suddenly become polynomial. Now, my question is actually, have you or do you know of any research where they looked at the maximum special cases of resource constraint project scheduling, the maximum special cases under which conditions you maintain polynomiality, and you can come up with some algorithm that, and then a heuristic could become actually even useful in practice. Do you know of any research in that direction, or have you done any research in that direction? That fixed parameter tractability, that's very, very popular in Germany. In Germany and Israel, those are the two main countries that people are doing it.
To be honest, I hear about it the first time, but I'm curious to look at this. But I mean, what has the extreme case would be where you have a width of 1 is a purely serial network, and then of course it's
and the width infinity.
Solvable.
The width infinity is also the width infinity, so all the jobs have no precedence really. That's also very simple. The extreme cases tend to be
so I mean, there has been a lot of work done into this measures of the network, aggregated measures of the network, starting with the order strengths. Elmar Grabi has a long time ago has worked on this. And it continued. So recently, Van Hoeke and his team, they have published a set of new measures, and this is basically what they are looking at in how can we come up with a measure which aggregates information from the network such that this measure is as much has a good predictability in terms of. So it's more kind of it's empirical approach. It's not a theoretical approach. It comes up with a good predictability between hard and easy problems, always not from the theoretical point of view, but from the computer runtime point of view. So they have done a lot of empirical studies on this, and I think this is related to what you stated. So they would be interested to look at this.
Okay, thanks.
Okay, there is one question from YouTube, and it is copied to the chat. If I may ask you to open the chat and read the question.
Sure. See. Question from YouTube. Any known application of particle swarm optimization to solve FRCPSP using Kolisch and Hartmann schedule generation scheme with priority rule? Particle swarm optimization seems better than genetic algorithm to solve classical RCPSP. Not that I know of for the FRCPSP, but I haven't looked at all the literature, let's say beyond the classical review journals. I think that there might be something around in not strictly reviewed journals, because PSO is quite popular, and I mean people looking for applying different heuristic concepts to problems where they haven't been applied before. So I personally don't know any application there in any paper, but I think there's a good chance that there's same thing around. Yeah.
Right. Thank you. So, is there any other question? Not for the moment. Thank you very much, Rainer. I think it was a nice topic. RCPSP also is nice, at least to me. And I would like to mention the next talk, which will be given by Dries Gossens from Ghent University. And Dries will speak in 2 weeks about sports scheduling from consulting to science. So I would expect the other direction, but it will be maybe inspired by practical problems and experiences. So thank you very much for being with us, and hope to meet you in 2 weeks. Or you are always welcome to see it offline on YouTube. Okay.
Thank you very much.
Bye bye.
Okay, thank you.
Bye-bye.
Thank you.
Bye-bye.
Bye bye.